For this lesson, we're looking at operations with algebraic vectors. So I have an example here with two algebraic vectors, and they're currently in their ordered pair or ordered triple notation, where I'm going to turn those into their unit vector notation here. So vector u would be 1i hat plus 3j hat minus 4k hat, or cap if you prefer. And vector v would be equivalent to 6i hat, 8j hat, plus 8j hat, and then plus 2k hat. So if I want to add those together, so vector u plus vector v, we can take their components, their unit vector notations and add them together. So 1i hat plus 3j hat plus minus 4k hat, and to that we're adding 6i hat plus 8j hat plus 2k hat. And when we put those together, it's like collecting like terms here. We have 1i hat, and then we're adding 6 more I hats. So we're heading in the x direction, 1 unit and then 6 more units. So altogether we've gone 7 units along the x. And then the j's, we have the 3 plus the 8, that would be 11 j hat. And then a minus 4 and plus 2 would be minus 2k hat. Turning that back into the ordered triple, we're going to have 7, 11, negative 2. Now we don't have to go through the process of changing them all to the unit vector notation. We can just look at the components. So really what's happened here is we've taken the x components, the 1 and the 6, and we've added them together to get the 7. And we've taken the 3 and the 8 and added them together to get the 11. And the minus 4, add the 2, gives us the minus 2. So quickly then, our vector u plus vector v really will just get us our new vector by doing the sum of the components here. So 1 plus 6, 3 plus 8, and then negative 4 plus 2. So that's the more efficient way to do this, which gives us the 7, the 11, and the negative 2. All right, so our second example here involves some scalar multiplication as well. So we want 3 times that vector u. So we're going to have 3 times this vector. And when we do that, we're just going to multiply each component by 3. And then we have minus 8 times vector v. So 6, 8, 2. So multiply that 3 through the vector. We're going to get 3, 9, and negative 12. And then we're going to take away 8 times 6 is 48, 8 times 8 is 64, 8 times 2 is 16, and then we can subtract those components. So 3 take away 48 is negative 45, 9 take away 64 is negative 55, and negative 12 take away 16 would be negative 28. So it's just some basic algebra with the vectors. So I've outlined here in the bracket, in this table, the scalar multiplication. So when you have a scalar, and as a scalar, and you multiply through the bracket, you're just multiplying each component by that scalar. Similarly, if you have a scalar multiplying the vector in its unit vector notation, you're just going to multiply each of those coefficients by the scalar in front. To add 2 vectors together, you're really just adding the components together here. And similarly with the unit vector notation, you're just adding the coefficients of each of the unit vectors. All right, using vectors demonstrate that 3 points A, B, and C are all collinear. So first of all, you need to know what collinear means. It means they lie in a straight line. They form a single line. So we'll write that down. This means that if we look at the pieces, if we look at A to B as a vector, then that vector would have to have the same direction as A to C. They would have to run parallel to each other and in fact coincident. Likewise, B to C would also have to have the same direction. So let's summarize that here. So let me just explain this statement that this means that vector AB and vector BC run either in the same or opposite direction. So let's say you had A to B, and these are not the points that I've given you. I'm just giving you some points. And then you had C over here. If I do B to C and they don't form a straight line, do you see that the they would not have the exact same direction, so the vector itself would be entirely different. But if they did run the exact same direction, they don't have to be the same length, and in fact it could be the opposite direction. So let me just make a new C here. They might be different in length, but since they have the same direction, they would just be a scalar multiple of each other. I could also maybe have C down here, and then B to C would run the opposite direction to AB, vector AB. So we're really looking for, or to prove that things are collinear, you want to show that vectors are scalar multiples of each other. So let's look at this as a question of what vector AB looks like. So you might recall from a previous lesson that if I have AB, that's really AO plus OB. So it's just the working backwards of what we had learned in the very first unit. Now AO, I don't know that, but I know OA. So I'm going to change AO to negative OA. And I don't know if you can tell that those are separated from the equal sign. I want that to be negative OA. So that's going to equal negative OA plus vector OB. Or you can think of that as vector OB minus vector OA. All right, so if I look at OB, vector OB is the negative 3, negative 13. Vector OA is 4, comma 1. And then when I subtract that, I get negative 5, comma, negative 14. Just kidding. No, I don't. I don't get negative 5. I get negative 7 there. Sorry, negative 7, comma, negative 14. So that represents vector A to B, joining A to B. If I take a look at B to C, again, I could run through this whole thing, but the key idea is if I want vector B to C, I'm really taking OC and minusing OB. So I take the second one and subtract the first one to get that vector. OC would be 11, comma 15, and we're going to subtract negative 3, comma negative 13. That's going to give us, that's a subtract in between, so 11 take away negative 3 would be 14. 15 take away negative 13 would be 28. So if I look at these two vectors, this 14 and negative 28 would really be this vector multiplied by negative 2. So this really is negative 2 times vector AB. So we do have a scalar multiple, and therefore we know that they have the same direction and the 3 points will be collinear. So our criteria for collinear or parallel vectors is that one vector has to be a scalar multiple of the other vector, which just means if you've got a vector u, that is just k being our scalar, k times vector v, vector the other vector. Okay, so k is just scalar here. Struggling. Here we are. So k is scalar. All right, I'm going to start a new video for the next page.